I'm your host G. Today we're going to discuss integration. Integration is a wide-ranging tool throughout mathematics, and you'll learn to use it easily with me. All the cool kids talk about integrals, and some try to throw them at every problem. And I get it, integrals are scary the first time you learn them. Without help, you may get stuck in revolutions. I'm here to pull you out of those revolutions into larger and larger domains. Who knows, with enough pulling, you may become the next Leibniz. And at this point, you've probably caught on. I'm not a Sheafification of G. And with that irreducible expression off my shoulders, let's dive into integration. Before we discuss integration, we must first approach and understand Riemann sums. Riemann sums depend on partitions of a function, or separated equal length segments. These partitions have a given length, delta x. The first partition is called x star 1, the next partition is called x star 2, and so on. As all partitions are of equal length, each succeeding partition will have a delta x larger x value. The idea of these partitions is to create rectangles that approximate the area under a function, with a lower bound of 0 for positive functions. This is known as signed area. The height of the partitions is f of star k, where f is a function we are approximating the area of. When we have chosen a given length for delta x, we will then calculate all partitions' area and add them. The goal of the addition of the area of these partitions, called the Riemann sum, is to get smaller and smaller values of delta x for more accurate approximations. How are Riemann sums connected to integration? Riemann sums are connected to integration through definite integration. Definite integration is the operation of finding the exact area under the curve of a function. So it can be seen that the Riemann sum is an approximation to definite integration. As definite integration is a bounded version of indefinite integration, the Riemann sum is just an approximation of integration. Why is integration the inverse of differentiation? Well, in the case of continuous functions, the Fundamental Theorem of Calculus proves that when applied to each other, they return the original function. The proof depends on the idea of partitions, which we discussed before. The proof goes like this. The area under the curve between f of x and f of x plus h can be found by finding the difference between the area function of x plus h and x. This approximately equals f of x times h, so f of x approximately equals a of x plus h minus a of x over h, which is the derivative of the area function, a of x. The most common way to notate integration is the Leibniz integral, or this S-looking integral. Leibniz made his integral look like an S to represent that integration is basically just summation. Also, Leibniz notation for calculus is in general way more popular than Newton's. Now that we've discussed Riemann sums and definite integration, let's move on to antiderivatives, or indefinite integration. When integrating, there are a few tricks to keep handy. First, there's a power rule. For any polynomial function of the form x to the n plus x to the m and so on plus x to the a, its antiderivative will be x to the n plus 1 divided by n plus 1 plus x to the m plus 1 over m plus 1 and so on plus x to the a plus 1 over a plus 1. There's also the rule that if a function inside an integral is multiplied by a constant, that constant can be taken out of the integral and can multiply the entire integral. This is handy for stuff like integration by parts. Fun fact! The indefinite integral of e to the x is itself. Other tricks for indefinite integrals are that the integral for 1 over ax plus b is 1 over a times the natural logarithm of the absolute value of ax plus b. The indefinite integral of e to the ax plus b is 1 over a times e to the ax plus b. Even though some continuous functions do have elementary antiderivatives, most don't. What is an elementary antiderivative? An elementary antiderivative is an antiderivative that can be expressed in terms of elementary functions, such as logarithms, exponentials, and trig functions. When a function doesn't have an elementary antiderivative, use approximation methods such as Riemann sums. There are also the Newton-Cotes formulas to approximate the area under the curve. Most usually, the closed form expression of the second Newton-Cotes formula, otherwise known as Simpson's 1/3 rule, will be used over the other closed form expressions of Newton-Cotes formulas to approximate the area under the curve, because it is highly accurate and easy to use. Let's discuss Simpson's composite 1/3 rule. For a definite integral with lower bound a and upper bound b, Simpson's composite 1/3 rule is as follows. Assume h equals b minus a over n, where our function is divided into n partitions, where n is even. Then, the area under the curve is approximately 1/3 h times f of x0 plus 4 times the sum, upper bound in half, index I equals 1, f of x, index 2i minus 1, plus 2 times the sum, upper bound in half minus 1, index I equals 1, x, index 2i, plus f of x n, where x sub I equals a plus ih. Here's an example. The integral from 3 to 8 of 1 over the natural logarithm of x, which has no elementary antiderivative. As n equals 8, a equals 3, and b equals 8, h equals 5 over 8. F of x sub 0 equals f of 3, which equals 1 over the natural log of 3. The next term, or I should say sum, is 4 times this lengthy mess, which is approximately 9.83995. The next term, or sum, is, again, this lengthy mess, which approximately equals 3.602813. The next term is f of 8, which is approximately 0.480898. Adding these all together, they will add up to 14.83389922266. Then we multiply that by 5 over 24, or h over 3, which approximately equals 3.090395672221, which is highly accurate to the actual area. Only about 0.000479 off. The error bound for the composite Simpson's rule has an n to the 4 term in its denominator, so doubling the amount of subdivisions or partitions used results in 16 times higher accuracy.